the higher tear only. Bits of this can apply to a foundation and obviously triple as well. So why atoms bond together? Have you ever wondered why, if you look at the periodic table, that group 1 to 7 elements are bonding together? And the answer is to get a full outer shell. Now, how do you get a full outer shell and what are the number of electrons? Have a think. So, full outer shell is where we're looking for 8 electrons in the outer shell, which gives you the noble gas configuration. And what we're going to look at today, how do these atoms get a full outer shell? Now, you must know from the previous PowerPoints that if you are a metal, the outer shell is namely empty, so it's easy for them to lose electrons than gain because of the ionization energy that's needed. So if you live in group 1, you will lose 1 electron, group 2 will 2, if you're in group 3, you lose 3. Now 4 is quite interesting because you can lose or gain 4. In comparison to nonmetals, which have rather full outer shells, so it's easy for them to gain electrons. And if they gain electrons, then they gain negative charges. So chlorine is in group 7. It's easy for it to gain 1 electron. Sodium, sulfur's group 6, -2 charge, is easy to gain 2. And if you look at noble gases, it doesn't lose again because it's already got full outer shell. So they don't tend to react with anything because they don't need to gain or lose electron, like I said. Now, ionic bonding. There's 3 types of bonding you need to know. Ionic bonding is the first one. It's the bonding between a metal and a non-metal to obtain a full outer shell. Now, as you can see in the diagram, I've taken an example of sodium and chlorine. So in the first diagram, you'll see sodium's got 281 configuration, and as discussed in the previous slide, we need 8 electrons in the outer shell to be stable. So sodium quite happily will lose 1 electron. Chlorine lives in group 7, hence has 7 electrons in the outer shell. It needs to gain 1 in order to become stable and get a full outer shell. So when sodium loses 1 electron, it becomes a sodium ion. It's really important in the exam to state it's now an ion and it has a +1 charge. And so does the chlorine. It becomes chloride ion. So it's Cl minus, got -1 charge. Those charges are indicating how many electrons have been lost or gained. Looking more in depth, and when it becomes slightly challenging for students, if it's not 1-to-1 ratio, in this example, you got magnesium that lives in group 2, wants to lose 2 electrons and get 2+ charge. Chlorine that lives in group 7 needs 1 electron only. Now, you will notice that I have got 2 chlorines, and the reason being 1 chlorine can only accept 1 electron. However, magnesium's got 2 to lose, hence the ratio is 1 to 2. So the formula becomes MgCl2 because I've got 1 magnesium and 2 chlorines. Now, in summary, ionic bonding. Metal atoms give all 1 or more electrons to nonmetals. Metal atoms become positive ions and they are called cations. Now, cations can be remembered by imagining cat's eye makes a positive sign. The nonmetals become negatively charged and they become anions because they're gaining electrons. So, what is giant ionic lattice? Giant ionic lattice is these structures in front of you, and these structures are of sodium chloride, and they show that in this picture you have got equal positive and negative ions, and they are surrounded in a 3D structure. So for each positive you have a negative ion next to it. Now, because they are held together quite strongly with electrostatic forces, that means air has a high melting point, which then means you need to put in a lot of energy to break those bonds. Now, they do not conduct electricity as solid, because if you plug two electrodes in a power pack into a solid sodium chloride structure, electricity can't flow. There's no free flowing ions because everything's been held together in a structure. However, if you was to melt or dissolve this structure in water, you then have free flowing ions that carry the charge, hence they conduct the electricity. Right, what other types of bonding are they? Let's have a look. The next type of bonding we're looking at is covalent bonding, which is a bonding between non-metals only. So it can be two or more non-metals joined together to get a full outer shell configuration of 8 electrons. And it's quite easy to remember covalent because co means sharing, so bonding, like so just represent the type of bonding where you're going to share. The examples you need to know for the GCSE curriculum is hydrogen that has 1 electron in the outer shell. They share one each and become H2. Oxygen will share 2 pairs of electron because they live in group 6. So you will see that oxygen has 2 lines because they're sharing 2 pairs of electron, one here and one here. And then chlorine shares 1 pair of electron, becomes a Cl2. Looking at further examples, here's H2O, a structure of water molecule, and NH3. And what you're looking at is here multiple non-metal sharing. Now, oxygen lives in group 6. It needs 2 electrons to get full outer shell, and hydrogen in 1. So you can see the hydrogen is quite happily sharing this one here and then here. However, if you're to then count all of the oxygen ones, then you will count that there are now 8. Now, so nitrogen lives in group 5, so it's got 5 electrons, the red dots. However, to get a full outer shell configuration, it's going to share 3 pairs of electrons because it's in group 5, and you represent that by 3 lines. You can see there's 1 pair here, 1 here, and another one here, and then this gives NH3 a full stable structure. Looking at the properties of simple covalent substances, the word simple doesn't mean they're weak. The covalent bonding is extremely strong within the molecule. However, the intermolecular forces are weaker within the molecule. So they don't conduct electricity as covalent bonding because they do not have any free-flowing ions to carry the charge. And because it's a simple molecule, they have a lower melting and boiling point, which means they don't need to overcome a strong intermolecular force to break the bonds. In comparison to simple molecular substance, we're going to now look at giant covalent bonding. Giant covalent bonding is also known as micro molecule, which they can ask in the exam, so you should know what that word means. Here's the structure of diamond. Now you know diamond is extremely hard substance because it has a continuous chain of carbons. Each carbon is bonded to another 4 carbon. They don't conduct electricity, does not have any free-flowing ions. Extremely hard structure, like I said, because of the covalent bonding. And they have high melting and boiling point because of the strong bonds. Now, you normally get a question in the exam to do a comparison of diamond compared to graphite, which are both allotropes of carbons. So graphite also giant covalent molecule. However, if you look at this structure, only 3 carbon atoms are bonded, and you will see this dotted line here. This dotted line is basically representing the delocalized ion. So this one here is delocalized electron, and you'll see each of these have got 3 bonded and 1 delocalized. That means it's free to move. Now, because of this delocalized electron, there are gaps, and the structure is